Hello everyone, welcome to this video on standard deviation and z-scores. Standard deviation and z-scores. Okay, so let's consider a data set that consists of the thickness in the ozone layer, which is measured in Dobson units, and that's going to represent our data set. Okay, X representing each piece of data. So let's say on day 1 of the week that's being considered, it's 152 Dobson units. And then day 2 is 158. Day 3, 151. Day 4, 153. Day 5, 159. Day 6, 158. And finally, the end of the week, day 7, 152. Okay, so step 1 for standard deviation is calculating the mean. So we need the sum of the data. So in this case, the sum of the data equals 1083. Okay, so let's work that out on the side. The mean, which is the sum of the data set divided by the size of the data set. So in this case, 1083 divided by 7 is 154.71428, and it continues. It actually repeats, but we're going to round off to 1 decimal place. So that means it's going to be approximately 154.7 Dobson units is the sample mean for this data set. Okay, fantastic. So that's the first step. Calculate the mean. In this case, the mean thickness. Step 2, we need to calculate the deviations from the mean. So we're going to add a column to our chart. Okay, we're going to add a column. In fact, we're going to need 3 columns. So let me make some room here. And let's put a 3rd column in here. So this first column is going to be the deviation. So you take each piece of data and you minus it by the mean. And that's called the deviation. How much does the data deviate from the mean? Okay, then the next column, we're going to take that deviation and we're going to square it. Okay, so the squared deviation. Okay, so row 1, it's going to be 152 minus the mean that we calculated, 154.7. 154.7, and in this case, the answer is negative 2.7. And while it's on our calculator screens, we're going to square it. So negative 2.7 squared, and that's 729. So step 1 is calculate the mean. Step 2 is calculate the deviations. Step 3 is to square the deviations. Okay, so let's repeat this for all of them. Okay, so the next row, 158 minus the mean And in this case, it's 3.3. That's how much this piece of data deviates from the mean. So it's on the right side of the mean. If it's positive, it's on the right side of the mean. If it's negative, it's on the left side of the mean. And while we have on our screen, we're going to square it, and that's 10.89. Okay, next row, 151 minus the mean. In this case, it's going to be negative 3.7. And when we square that, 13.69. And then 153 minus the mean, negative 1.7, squared 2.89. And then 159 minus the mean, 4.3, squared is 18.49. And then 158, which we've already calculated up above, 3.3 and 10.89. And 152 was the first one that we calculated, negative 2.7 and 7.29. And at this point, a nice thing to do is check the sum of your deviations. So the sum of the deviations. And typically, this is a good indicator if your calculation for the mean is true, because the mean is the average of all the values. So we've taken the sum of all the values and we've distributed them evenly across 7 values, which leads us to a mean of 154.7. So it's the average of all the values. So if we take the distance, the deviation that each value is from the mean, and add them up, the answer should be 0 theoretically. This answer should be 0 theoretically, because that verifies that the mean of 154.7 is true. So that's what should happen theoretically. Now, because we rounded off to 154.7, in this case, when we take the sum, it equals 0.1. And that's approximately 0. Had we not rounded off the mean over here, had we not rounded this off, we would have had a sum of exactly 0. So this gives us some confidence that our calculation for the mean is true. And our squared deviations have some validity as well now, knowing that our deviations sum is true. Okay, so let's move on to the fourth step, which is to take the sum of the deviations squared. So this third column. So the deviations were squared, and we're going to take the sum of that column. So the sum of this third column. And in this case, it's 71.43. So this is the fourth step in calculating the standard deviation. And this is not the short version of the calculation, which I showed in another video, the computational approach. This is the approach where we calculate each deviation from the mean, then we square that value, and then we take the sum of the squared deviations. The sum of the squared deviations. Okay? Next, we're going to calculate something called the variance. Okay, so to do that, lowercase sigma squared is the symbol for the variance. Okay, and that calculation is the sum of the deviations squared, which we just completed, the sum of the deviations squared divided by either the sample size or the population size. So typically for the sample size, you divide by n minus 1, and if it's sample data, and if it's population data, you divide by n. So because every day of the week was included and they were targeting this week, we'll treat this like population data. However, if we were considering the whole year of thickness of the ozone, then this will be a sample of the whole year. But let's take this as 1 year was the focus, which means it's population data because every day in the week was included. So we'll divide this by n, and this answer is called the variance. So in this example, it's 71.43 divided by 7 days of the week, which gives us a variance of approximately 10.204, and it continues on our screen. And that is the 5th step in the process of calculating standard deviation. And now finally, the last step. If you take the square root of the variance, the answer is standard deviation, which is lowercase sigma. Okay, that is standard deviation. So what are we actually calculating? We have taken the deviations, we've squared them, we found the sum of the deviation squared, we divided by n to calculate the variance, and now we're going to square root that to calculate the standard deviation. Okay, so in this case, it's going to be the square root of 10.204, and I still have it on my calculator screen, which becomes 3.1944 ... It continues, and if we round it off to the first decimal place, we could say that the standard deviation is approximately 3.2. And this is in the units of the data set, which is Dobson units. Okay, so we've got standard deviation calculated in 6 steps, where every single data point was taken into consideration, and it's deviation from the mean. Okay, so that is standard deviation. Next, let's talk about z-scores. So to talk about z-scores, first of all, what's the formula? Okay, so z-scores is a calculation which is the deviation. So whichever data piece you're considering, so you take that piece of data, you minus it from the mean, and you calculate the deviation, and you divide it by the standard deviation. Because z-scores is the number of standard deviations a piece of data is from the mean. So in this case, let's take, for example, the 3rd day of the week was 151 Dobson units. And if we minus it from the mean, 154.7, and we divide it by the standard deviation, 3.2, this becomes, let's calculate this, so 151 minus 154.7, that leads us to a deviation of negative 3.7 divided by the standard deviation of 3.2 divided by 3.2, and that equals negative 1.15625. And we're going to round this off to 2 decimal places, which is negative 1.16 standard deviations from the mean. So the z-score for the 3rd piece of data, so I'll call it Z3, is negative 1.16. What does this tell us? This tells us that the piece of data, so if we took a number line and we put the mean on it, and we put the value of 154.7, and then 151 is somewhere on the left. And in terms of standard deviations, it's negative 1.16 standard deviations from the mean, which means it's on the left of the mean. And visually, you could see 151 is on the left from the mean. Why is this helpful? Because it becomes a standard comparison between different data sets. So for example, if in data set 1, let's say in 1 week, In the week that we considered, we know the mean is 154.7 Dobson units and the standard deviation is 3.2 Dobson units. But let's say, call this week 1, but let's say in week 2, let's pretend in week 2 the mean is 156.2 Dobson units and the standard deviation is 3.7. Let's pretend. So now we can compare where this piece of data falls within the data set. So if in week 1, the third day was 151 Dobson units, and we just calculated the Z-score, it's negative 1.16. In the next week, we'll call this week 2, let's pretend the third day was also 151 Dobson units. But in the analysis of that week's aggregate values for the mean and the standard deviation, it might fall differently. So let's calculate it. So 151 minus 156.2 divided by 3.7. So there's a higher average in the second week for the Dobson units for the thickness of the ozone layer. But let's see where this piece of data falls within the spread of the data. So negative 5.2 over 3.7. And this becomes negative 1.41 approximately when you round it off to 2 decimal places. So you can see in week 2, the same thickness of the ozone layer is further away from the mean thickness. It's more to the left. So when you're comparing data sets, this becomes a standardized comparison between the values, because the standard deviation is the average distance of the scores from the mean. And when you use Z-scores to represent a value, it can be compared to other data sets more efficiently. So that wraps up this video on standard deviation and Z-scores. Thank you for watching. See you in the next video. Press like, press subscribe if you want to be alerted to future videos. Leave a comment in the comment box below so we could see and hear what you're thinking about our videos, and if you want more videos or if you want other topics or other questions, etc., let us know. You guys are awesome. Have a great day. Thank you.